In this video, we'll talk about two main themes. One of this, which is related to mechanism from the wave equation, and then the other one will be focused on Sn1 and Sn2 mechanism. And the Sn1 Sn2 is actually only for Edexcel example. But then for wave equation and mechanism relationship, which is like required in every example. Yeah. So for the first thing, in a reaction, there actually can be more than one step in reality. But then if there are more than one step, then how people decide which one is the most important for the reaction rate, then people will consider that as like the slowest one. The slowest step will control the overall rate of reaction. Therefore, people will call the slow step, which is the rate determining step. But then the reason for why the slow step is the most important one, then you can refer to the diagram here. Just like a filter, then you have so many filters, then actually the overall rate of the filtration is just depending on the slowest filter, which is here, or you can here, or you can say here. And then actually, not necessary to be like the step one is the slowest one. It may be step 2 or even step 3. Just the slowest one will control the overall rate. Even the other filter may be like really big, but then it doesn't affect the overall rate. So people will consider that all the time the slowest step will determine the overall reaction rate. And it can be the first one or second one or third one. But then just how you can deduce if there's any 2-step or 3-step mechanism, or it's actually only 1 step, then we can refer from 2 different relations, and then those is like frequently asked question in a real exam. Then from the overall equation, we can see, take this example, you can see there's like so many particles here, right? It's like 5. Then technically, it's like impossible to have a collision between 5 particles at the same time. So from the overall equation, we already can deduce that the mechanism should be more than 1 step. But then there's like one more reason is after you know the wave equation, and then assume that this time the wave equation only depends on A and C. Then you can see that only A and C is affected, and then they're first order only. So you're actually missing one of A and one C and also B. Because if B is not in the wave equation, that means they cannot appear in the rate determining step. Therefore, you have to decide another step to include B. Therefore, we can say that it's like the mole of the particles in the wave equation cannot match with the thing in the overall equation. Therefore, there should be more than one step in the overall mechanism. Then some relationship that you have to do a linkage is like you have to know how to identify the rate determining step from the mechanism, from the suggested mechanism. So just take this case example. Maybe from the first part, or maybe from the question, they may told you the wave equation already, and then they may told you the suggested mechanism also. Then from the 2 information, then you can say which one, if they include all the information from the equation, then they are the rate determining step. Therefore, you can see that step 1 is already included A already. Therefore, step 1 will be the rate determining step. Other than they will include A, then the mole of A or the number of A, it has to be equal to the order of A. Therefore, if A here is like second order of reaction, then here should be 2A inclusive. So if A, okay, they change it in the first order, so step 1 should only include 1A only. Therefore, other than the chemical has to match, and also the coefficient also have to match with the order of reaction, then you can say step 1 will be a rate determining step. And then most of the time, if your mechanism involves so many steps, there should be something called intermediate formed in step 1. And then how do you know they're intermediate or the overall product from the reaction? Then you can see one thing is like if they formed in step 1 and then using as a reaction in the second step or first step or the other step, then they're intermediate. Because in the overall equation, you can see it's like the E here and here will cancel out. Therefore, you can't see no E in the overall equation. Then they are the intermediate. Yeah. They are something formed from step 1, but they're not a final product. It means that you will reuse it in second step or some other further step. And also one more like special point or tricky point is like the overall equation maybe only include one A, but actually the rate equation you can have second order of A, because you can using 2A in the rate equation, but then just you have to regenerate one of the A in the last step. Then to find out the overall equation, then you can eliminate one of the A also. So only one A is used in the overall equation. Yeah. So order of reaction may not match with the coefficient of the overall equation, but then order of reaction has to be matched with the rate equation coefficient. That's the most important hints when you predict the mechanism. Then another example here is like this time we are having a mechanism already, and then someone has told you the slow and the fast already. Then you can do a reverse action, then deduce the mechanism. Deduce the rate equation from the mechanism. And then obviously most important thing that we're concerned about is like the slow step, and then here it's like 2NO2. Therefore, I would say the reactant side will give you an idea about the rate equation. So NO2 only here, then I would say only related to NO2. And then 2NO2, that's why I'll put the second order in here. That means at the same time, you can't see any carbon monoxide in the slow step. That means the rate equation here is like 0 order with CO. Then obviously I can do another example. It's like if I change it into, okay, the first one is fast, and then the second one is like slow. Then this time the step 2 become rate determining step. Then at the first point I can say the rate is equal to K times NO3 and then times CO. But then this one cannot be a final answer, because I would say NO3 is an intermediate of the mechanism, because you can see that it's like you form NO3 from step 1 and then you reusing it in step 2. And then we can't write an intermediate in the rate equation. You may think the main reason is like rate equation gives you a hint about how you control the amount of substance that you add in order to control the rate. Then obviously you can't add intermediates, because intermediate is like something that you form from step 1, from the previous step. So you can't adding it, then you have to rewrite it into something else. Then how do I know how to rewrite? Then you may think the concentration of intermediate, which is NO3 in this case, it should be proportional to the reaction rate of step 1. Then reaction rate of step 1, then we can say that it's like rate is equal to K times NO2 square. Then I can substitute the whole thing here to replace NO3. Then I can rewrite the equation like that. Then you think there is like so many K in here, but then you can just combine into just one rate constant. That's already fine. Because in rate equation, we're not really concerned about the value of rate constant, just a constant. The most important part, the only important part that we're concerned about is like whenever you know the order of reaction of each reactant. So once you rewrite it, then you can replace the NO3 with NO2 and then square. Then we can know that NO2 is second order and also CO is first order. So you may think if like the mechanism is having a slow step at the second one or the third one, or just not the first one, there must be some intermediate included. Then when there is an intermediate, then you have to rewrite into a reaction rate of the previous step. Therefore, you can using some other reactant to replace that. You can using some other reactant before to replace the intermediate. That's the most important characteristics when you deduce the rate equation. Yeah. And then you may think if the mechanism are using the last step as the slow step, that means every reactant will be involved in the equation, because you will keep on replace the intermediate by the previous reactant. So technically, every reactant should be involved. And reversely, if your first step as a slow step, then this time there should be no intermediate at all, because the first step only would having a reactant that you really add, no intermediate you can use. So you think here are some kind of characteristics, like if the first step is slow, then no intermediate at all. If the last step is slow, then every substance are involved. And then the order of reaction will be just really equal to the coefficient, to the equation, to your overall equation. But then technically, it's not 100% correct. What I mean is like coefficient of overall equation not necessarily give you the order of reaction. That's why we have to do the experiment to find the rate of reaction when you change the concentration of substance, and then to find the order of everything. And then other than deducing the mechanism or deducing the rate equation, another important thing that like I think haven't come up in the previous exam, which is drawing an energy profile when there's like multi-step mechanism. But actually it's not very difficult. You think just good characteristics like you will have so many steps, then you have to draw so many active rate energy. Then how you notify which one is like slow or fast, then using a different active rate energy to represent that. And then obviously the highest one will be the slowest step. That's why you just have to draw a higher active rate energy to represent that the one is a slower in this case. And then when you draw energy profile, then you have to write down the x and also y-axis. And the x-axis are then the reaction coordinate. Another wording that you can use is like reaction progress. Then obviously both wording are fine. Yeah. But then just make sure you can using a correct relative value of active rate energy to notify they're slow or fast. And obviously if the step 2 is like slow, then you can just draw it like that. Then with a higher in step 2, higher EA, then here will be the EA2, which is higher than the EA1 here. And then the last thing for this rate mechanism is like you have to predict the mechanism by yourself. It's also a common question, especially for like OCR and also AQA. Yeah. And then obviously you will know the rate equation first. Maybe you will solve it in part A, or maybe they told you already. Then from the rate equation that given you, then you will know one thing is like the reactant. Because you can match here, we have the reactants already. And then you can see that only one NO2Cl is included. That means another NO2Cl will be using in the first step. Then how do I know how many NO2Cl? Because you know the overall equation, then you know how many reactant that you should use in one reaction. Therefore 2 NO2Cl is like adding it, then one of it is slow, the other one is fast. Then how you predict the product side, then you may think most of the time for step 1, you should form something as a product and then something as an intermediate. Then the intermediate will continue to use in the step 2. Then how you decide which product that you're going to form, then actually just you can check the equation and then try to check the balancing. Then you will see that you only can form NO2 because the right hand side you don't have enough amounts of chlorine, you don't have Cl2, so you can't form Cl2. So reverse it, you can form Cl as an intermediate and then reuse it in here, and then you can form one NO2 as one of the product. And then if this one is like product already, then just no need to reuse in step 2, but then just Cl as an intermediate, then just make sure that they will appear in the fast step again, and then react with another NO2Cl. Yeah, that will be an important point when you need to write the rate equation, when you need to write the mechanism from rate equation. And here will be everything about array, equation, and also reaction mechanism. And then next part will be like Sn1 and Sn2, which is called nucleophilic substitution mechanism. And then those things are just only included in Edexcel only. But I would say here is like important part, but then just for Edexcel. Therefore, if you are in OCR or in AQA or something else, then this part is actually not like relevant at all. Yeah, because you won't learn different mechanism for nucleophilic substitution. You will just learn one thing, but just only Edexcel will do it in the separate doctrine. Therefore, if you're studying in Edexcel, then technically in AS you learn nucleophilic reaction already. But then just at that point, they will just tell you you're using primary halogen alkane, and then you only have one type of drawing, and then the drawing should be similar to something like that. But in here, in A2, then they will teach you another style. It's like when the compound is a tertiary halogen, then the mechanism is like totally different. And then they will be called Sn1 and Sn2. But then no matter how you draw the mechanism, you may think they're like similar in certain direction, which is the arrow here. You always have to draw the arrow for this one and also this one. You always have to include those arrows, because no matter how you draw the mechanism, then the reaction, the style is like that. You can break down the halogen and then you replace with the hydroxide in order to form alcohol. But then just Sn2 will combine the two arrows at the same time. Then Sn1, you just do the arrow like step by step. Therefore, Sn1, although there's like one here, but then technically there's like two-step reaction. And then whenever there's like two-step reaction, then we can break down into like slow and fast. And then in here, you may think the step one must be slow. And then the only reason you can refer here is like there's a breakdown of the bonding. Then it should be an endothermic process. Then it should be like a slower process, because you can see here the step 2 is like you combine the two ions together to form alcohol. So technically this time you are forming bonds. So reversely it should be a fast step. Therefore Sn1, the 1 is not represented like how many steps. Technically it's like represent the order of reaction. Because if you see, if here the slow step only input one thing, which is the halogen alkane, then you can't see anything in hydroxide, right? That means only halogen alkane involved in the equation. That's why they're first order. So the 1 is actually the first order. And then Sn2, you may think they only have one step. So the two chemical, like the hydroxide and also the halogen alkane, are both involved in the mechanism. So the 2 represent the second order, but then just first order for each with like hydroxide and also halogen alkane. But then other than the kinetic stuff, then you also need to know like why different halogen alkane will favor for different mechanism. But then you may think like the tertiary idea is like really similar to when you predict the major product of electrophilic addition, which is also talk about the stability of the carboxyl ions. If you're tertiary compound, then you can form tertiary carboxyl ions, which is like much more stable than primary and also secondary. Therefore, tertiary will always like favor to form Sn1 mechanism, because they can form an intermediate, which is like a tertiary cation, which is like very stable. So reversely, primary halogen, they only contain one methyl groups, so they won't form primary carboxyl ions because like unlikely to form their like least stable substance. So primary halogen reversely will do some other reaction, and then they will form a transition state like that. And then primary halogen will favor to do that because here we have 5 groups. So if they have like less amounts of methyl groups, which is called bulky groups, then will be like favor to form, because this methyl group, then they will occupy less space, then they will have less static hindrance in the transition state. Therefore, you may think Sn2 is like for primary halogen. And the table here is like summarize some key points for the two mechanisms, and then both of it involving hydrolytic fission. And actually, you may think it's just other than free radical substitution, every time you draw a mechanism is like referring hydrolytic fission. You won't see homolytic anymore, except free radical substitution. And then we call Sn1 is like two-step, and then they will have tertiary, and then they form a carbocation in terms of intermediate. And Sn2 will be one step, and then for primary halogen alkane, and then they will form a 5 groups for intermediate for transition state, which is something like this. And then the kinetic stuff, just like what I said, like Sn1, the 1 is actually representing the order of reaction, which is only halogen alkane and involved. Because the first step is slow, here is like fast. That's why you will draw a mechanism which having a first step with a higher active HAG to represent their slow. And then actually the whole name of Sn1 is very long, because as a substitution and as nucleophilic, then how you call 1, actually people will say unimolecular, representing the number of reactant in the rate determining step is 1 only. Now for Sn2, the 2 represent their bimolecular reaction. There will be 2 particles in the rate equation in the rate determining step. Yeah, because they're one step, so the one step must be rate determining step already. And then there's like 2 different particles here, so they will call bimolecular nucleophilic substitution. And here that means both of it are involved in the equation. That means a tricky point is like most of the time, if you increase the concentration of substance, you can increase the rate. But then in halogen alkane substitution, when you increase the con of hydroxide, you may not get an increased rate when you talk about tertiary halogen alkane, because they're independent with the hydroxide concentration. Because for hydroxide, they're like 0 order of reaction. That means even you change it, there should be no effect at all to the rate of tertiary halogen.